and simple harmonic motion is what this is about. Oscillating systems. SHM is a common abbreviation for simple harmonic motion. This is really what this is based about, the fact that we can often describe how things move in terms of this thing called simple harmonic motion that we're aiming for. Some formulae that then allow us to actually describe how something's moving, work out its position at a given time, work out its velocity at a given time, or its acceleration. So we're going to come up with some formulae that will allow us to do that and see how we can use them in systems like masses on springs. So if we look at the vibrations section of the booklet here, we can see a sort of definition at the beginning. All mechanisms and structures in engineering are capable of vibration. So if you give something a clout with a hammer, it will vibrate and you'll hear it ring. Okay? If you turn on a circuit that involves particularly inductors and capacitors, it will oscillate and then settle down. So when you disturb things, they tend to vibrate and then gradually settle down to some sort of steady state because of damping. So it's usually involved with some sort of damping. These vibrations or oscillations can be lessened by damping, which can be simply resistance from air resistance or friction. It can be a deliberate system like a shock absorber or dashpot with some sort of mechanical shock absorber type thing. And in this particular section, we're not going to be considering the idea of damping, just seeing how things move. So we set them moving and describe that motion. We're not going to worry about the fact that this oscillation is going to die away. So in other words, we're looking at a free vibration, which means that you get it going and then this vibration is allowed to continue unhindered. So a free oscillation can be represented by a sine wave like this, and it often is. In this particular picture, what we have is a situation where this is our sine wave, and what we do is we consider this thing oscillating in this sense, up and down here like this. So it's oscillating backwards and forwards in that sense, so in the y plane, and this represents time going by here. So if we think of something oscillating, it's starting here, it's moving upwards, and then it's moving downwards, and time is going by. And we're going to try and consider how this sine wave and the cosine wave, which is almost the same as this, it's just out of phase by 90 degrees, can be used to represent something that's moving in a rotational sense. So let's have a look at it. So some definitions first before we move on to that. We carry on looking through the notes. The period is the time which elapses while the motion repeats itself. So let's compare that with this diagram. So if we look at this, this is the motion from there to there, and then it starts to repeat itself. So what's the time period for this particular motion? You can see this, 2 pi, okay? So it's taking a time of 2 pi, 2 times 3.14, 6 point something if this was time seconds, to do one complete oscillation, that's what this is describing, one complete oscillation in just over 6 seconds. So half an oscillation in pi seconds, 3.14 seconds, and so on. So the period of oscillation is the time for one complete cycle. The frequency is the number of cycles completed in 1 second. A system performing free vibrations oscillates at what is called its natural frequency. So I give something a bash, it's going to oscillate at its natural frequency. There'll be some harmonics and overtones involved with it, like on a guitar string, which what gives it its flavour, that note. but it's got a natural frequency, and everything has a natural frequency. So that's what it will oscillate at. If I go back to this again, if the time for one oscillation is given by that period, there's got to be a relationship between the period and the frequency, which is the number of oscillations per second. So if the frequency was 1 hertz, what would be the period? So if the frequency is 1 hertz, the period is 1 second. If the frequency is 2 hertz, half a second. If the frequency is 3 hertz, a third of a second, because there's 3 in a second. 4 hertz, a quarter. So what's the relationship between the frequency and the period? It's an inverse relationship, with one going up and the other's going down, and the relationship is that the frequency is 1 over the period, which I think is probably a formula that you're familiar with. Okay, the frequency is 1 over the period. And we also have a relationship between the angular velocity and the frequency, 2 pi f, which too I think you're probably familiar with. Omega equals 2 pi f. And this angular velocity is suggesting that something's rotating to cause this frequency. So this is a frequency of something that's rotating. And I'm sure we talked before, or you've talked before, about this idea of this describing a complete oscillation or complete rotation of something from there to there. And so we can see a relationship between the sine wave and this rotation. And we're extending that idea today when we're considering the idea of simple harmonic motion. So we've got the frequency, we've got the period, and the amplitude. Just notice the deliberate spelling mistake there. Amplitude is the distance of either the uppermost or the lowermost points of the motion from equilibrium position. It's thus the maximum displacement. So if I go back to my picture of this cycle, which is here, then where do I measure the amplitude? It's from the rest position, which is taken to be here. So the amplitude is this distance, not from there to there, not from the lowest to the highest, but from rest position. So it's either from there to there, or from there to there, and they should be the same. So that's some definitions, some basic definitions, which hopefully you're familiar with. Now what we want to do is to try and think about this in terms of this thing called simple harmonic motion. So first of all, we need to consider it in terms of what it's to do with. So let's look at these first two statements. So this simple harmonic motion then, accelerations. We're talking about the accelerations of bodies. So if I take something like this, and then I, for example, attach a spring to it, either side, and then disturb it in this direction, backwards and forwards, as I pull it this way, then there's going to feel a restoring force trying to pull it that way. So as soon as I let it go, it's going to go back. It'll get to this midpoint here, this equilibrium position, and overshoot because it's moving and it's got inertia because of its mass. So it'll overshoot, and then there'll be a restoring force trying to pull it back that way, and so on. So it will oscillate backwards and forwards. And as we've discussed already, this oscillation will continue forever, indefinitely, unless there are other forces involved, which would be air resistance in this particular case. So if I set a system like this going in a vacuum, it will just keep oscillating backwards and forwards. And if I describe that motion, if I describe its motion in this x direction here, then I could do no better than drawing something like this. where this represents its position from that equilibrium position along here. So this would be the x direction along here, and this would be time, and that would describe perfectly this movement backwards and forwards. Okay, so we're going to use that to come up with some formulae so that we can, at any instant in time, let's say this thing's gone to there, I could say, given its position, how fast it's moving at that instant, what its acceleration is, or given its velocity and acceleration, where is it, stuff like that. I can describe exactly this motion and say things about it if I know how to describe it in terms of simple harmonic motion. And it's down to this. So the next part of this booklet is all about deriving these formulas. So we're going to have a look at that now. Okay? And it's to do with the idea of something rotating with an angular velocity omega, and also the fact that I'm interested only in what's happening to this body in the x direction. So as it's rotating round here, as p is moving round in this direction, what's happening to it, its distance from the rest position in this plane, in the x direction. So that's what I'm interested in. So the first thing to say is, well, this is a right angled triangle. And so, what's the length of this side? It's the adjacent side to this angle theta, and we know that side r, and so cosine of theta equals x over r. Cos theta from simple trigonometry equals the adjacent side is x over r. Okay, so that's the first formula you can write down. We're interested in what's happening to x, its displacement from rest position, so I can rearrange this formula slightly and get x equals r cos theta. So we can go a little bit further than that now, because I know what theta is in terms of the angular velocity of this thing. And we wrote it down at the beginning of today, actually. The angular velocity is theta over t, isn't it? You gave us that, Daniel. So rearranging that, theta equals omega t. So instead of theta in here, I can write x equals r cos omega t. And that's the first of the important formula we need to remember, use, to do with simple harmonic motion. So if I know r, and I know the angular velocity and the time, I can calculate its displacement from rest position at any given time. X equals r cos omega t. Okay, so this function represents this displacement. So this axis represents the displacement x, and this represents time, the x-axis here. So it's a bit disconcerting when you first see it. So the y-axis is actually representing the x displacement, and the x-axis is representing the time. Okay? And I put values for omega and t in, and I can change them. I can change r and omega. So r, if I increase or decrease r, what effect does it have on this thing? If I make r2, then it's starting at 2. So r is actually the amplitude. And if we go back to our notes and to this diagram, we can see that r represents the amplitude. If we look at this line here, if you imagine it coming round, at 0 time, it's lying along the x-axis, agreed? At time 0. So what's the x displacement? R, the value of r, because it's lying here. So at time 0, it's here. At time 0, it's here on the curve. So this is the x displacement on the x-axis here, and it's initially at the start point there, at the highest point it's going to be. So the amplitude R represents the amplitude. In this case, it's 2. And I can change that. Amplitude of 3. That means at time 0, it's starting at 3. Let's go back to 1, because we often take the unit R. So R equals 1, we've got that curve there. Does that make sense from this diagram? So if R equals 1, then at time 0, that displacement there is going to be 1, isn't it? So it's starting at 1. Now, let's consider this thing rotating. So omega is the angular velocity, the rate at which it's rotating. After a quarter of a revolution, it's at 0 along the x-axis. So after a quarter of a revolution, it's here. Okay? After a half a revolution, it's here. So it's gone negative on the displacement axis, and that fits in with this, doesn't it? After half a revolution, it's here. Negative sense. 3/4 of a revolution, it's here. A whole revolution, it's back to here again. And so that is corresponding exactly to this. So how long does it take for it to go right round one revolution? If omega is 1, which it is at the moment, there, then how long is it taking to go one complete revolution? It actually turns out to be, if I hit default axes, 2 pi here at this point. So if omega is 1, it's taking 2 pi radians to go a whole turn. Let's look back at our notes and some formulae we've got written down. Where are they? We wrote down some formulae. Frequency is 1 over the period. Omega equals 2 pi f. Omega equals 1. So what then does that tell us that the frequency is? If omega equals 1, frequency is 1 over 2 pi. If omega is 1, what's the period? 2 pi over 1. And so if omega is 1, the time for one revolution is 2 pi radians, which is this, 2 pi radians. It's reached that time after one oscillation. So that's if omega is 1. If I increase omega, what's going to happen to this wave? Now what's happening? Yeah, it's now doing 2 complete oscillations. One oscillation one oscillation there, because it's starting at the top. 2 oscillations there. So it's doing 2 oscillations within the time period, same time period of 2 pi radians. So if omega increases, the rate at which it increases, the time for one oscillation gets shorter and shorter and shorter, which you'd expect, wouldn't you? As I increase omega, the time for one revolution is getting less. I'm getting more revolutions in per second. So as omega increases, the frequency is going to increase, which is what this is saying. And as the frequency increases, the time for one oscillation is getting smaller and smaller, which is fitting in with our picture. So that's what's going on as this thing rotates. And we can calculate omega, because omega equals 2 pi f. So we could, if we wanted to, write this. And that's often done, because omega equals 2 pi f. So if I know the frequency, not the angular velocity, I can actually easily calculate what x is, knowing r. So those are useful formulae, and they can almost be grouped together because they mean the same thing, really. Okay? Okay, now, bit of calculus. We've got x equals r cos omega t. And I want to be able to find the velocity of this thing now. If I differentiate x with respect to t, what does that tell me? The rate of change of displacement with time is the gradients of the line, but what do we call it? What's the common word for the rate of change of distance with time? No, not acceleration. Daniel, you told me every day. What's distance, the rate of change of distance with time? Distance over time gives me speed or velocity. Yeah, okay. If I differentiate a function that's telling me the displacement and how that changes with time, then I'll get the velocity, the rate of change. So that's what I want to do.
You have to differentiate that.
Yeah. So what is this? dx by dt equals, who can remember how to differentiate that? Omega, James.
Omega.
Yeah.
R.
Yeah.
Sine omega.
Right, exactly right. The omega comes out, times us by the number in front, cosine changes to sine. Okay? And that's giving me the velocity. So now I've got a new formula to find the velocity. Velocity equals omega r, or r omega, it doesn't matter which way around you write it, sine omega t. So that's another one that's worth remembering. Not forgetting, of course, cosine differentiated to sine gives minus, yep, so that should be minus r. Yeah. So now, if we look at again at our triangle, our right angle triangle that describes this motion, so we've got something rotating, angular velocity omega, angle theta, so that's the angle through which it's rotated in the given time. We know this is x that we're after, and we know this is r. This side, from Pythagoras, from trigonometry, you can write down what this side is. This side, opposite side, so it's to do with the sine, is r times the sine of theta, which is omega t. So that's r sine omega t from basic trigonometry. Sine is opposite over hypotenuse. So I now know an expression for all three sides of this triangle, and Pythagoras tells me, what's Pythagoras' theorem? Yeah. The two short sides, a squared, or in this case x squared, plus r sine omega t squared equals r squared. So we can rearrange that to give us things that we're interested in. If I take the x squared over the other side, r sine omega t all squared equals r squared minus x squared. Square rooting both sides, r sine omega t equals the square root of r squared minus x squared, which is in your notes basically. Okay? But it's just from basic trigonometry and Pythagoras' theorem. And we do that because if we look at the formula we've just written down, this one, then we can see that r sine omega t is inside that formula. So we can replace r sine omega t with this, the square root of r squared minus x squared, and come up with another useful formula. So therefore, velocity equals minus r, or minus omega times the square root of r squared minus x squared. And that's another useful formula. So if you're looking at your notes, you might just want to put square bracket round it. Yeah. How do we find the acceleration? That's the rate of change of velocity. So differentiate the velocity function. So the relationship for velocity that we've got is minus r omega sine omega t. Differentiate that. dv by dt equals, there in front of you, bring the omega outside, minus r omega squared, whoops, cos omega t. And that represents the acceleration. So acceleration equals r minus r omega squared cos omega t. And that's another useful formula for the acceleration of this thing. However, if we look back to the very first function we had for x, r cos omega t. And if you look at this, we've got r cos omega t in there. So therefore, minus omega squared x. And that's another useful formula. You need to be able to use the formulae, but I also need you to understand where it all comes from, because it's to do with a rotation. It's to do with a rotating vector, this r vector that's rotating with an angular velocity omega. And that rotation is represented by a sine wave or a cosine wave. And so we can use that function, and we had it here, this cosine function, to represent this motion. So we can represent it in terms of some cosine wave. It's a free oscillation, so the amplitude of this wave is not decreasing. We're not considering that, remember. Okay? So it's telling us how this thing is moving with time. It's going from a maximum position at the start to a maximum position the other way, back to the start again, and so on, oscillating backwards and forwards with time, and this amplitude is not decreasing. So if we take that to be the case, we can write down the relationship between x and t. So that's the first formula to do with simple harmonic motion. We can differentiate that to get us a formula for the velocity. We can use a bit of basic trigonometry to come up with another formula for the velocity. And we can also come up with a formula for the acceleration by differentiating the velocity function, and that's basically what it's all about. And we end up with a series of equations that come in useful to solve problems.